Light does not choose the shortest path. It chooses the path that takes the least time. This simple idea, known as Fermat's principle, lies at the heart of reflection, refraction, and Snell's law. Let us begin with Fermat's principle applied to refraction. Here, light travels from point A in water to point B in air, crossing the interface at some point P. The speed of light is different in the two media, slower in water, faster in air. So the total travel time depends on where the light crosses the boundary. On the left, we see a graph of total time versus the position of point P. Every possible path corresponds to one point on this curve. Notice something remarkable. Among all possible paths, there is one specific path for which the total travel time is minimum. This is the path that light actually follows. Light does not minimize distance. It minimizes time. This is Fermat's principle. Now let us apply the same idea to reflection, where light remains in the same medium. Light travels from point A, reflects off the mirror, and reaches point B. The speed of light is the same everywhere. Once again, we allow the point of reflection to slide along the mirror. Each choice gives a different path, and a different travel time. The graph now shows total time versus reflection point. Notice that the minimum time occurs exactly when the angles of incidence and reflection are equal. This is why reflection obeys a simple geometric rule: angle of incidence equals angle of reflection. Reflection is not a separate law, it is a direct consequence of Fermat's principle. When the speeds of light in the two media are different, the same time minimization principle leads to refraction. And this gives rise to Snell's law. Let us now view refraction geometrically. Light is incident from water onto air. Angles are measured from the normal, not from the surface. As θ1 increases slowly, as the incident angle changes, three angles matter: the angle of incidence, the angle of reflection, and the angle of refraction. These values are shown live in the table. Notice two things. First, the reflection angle always equals the incident angle. Second, the refracted angle changes according to Snell's law: n1 sin θ1 equals n2 sin θ2. As the incident angle increases further, the refracted ray bends closer and closer to the interface. At one special angle, the refracted ray travels exactly along the boundary. This angle is called the critical angle. Beyond this point, refraction is no longer possible. When the incident angle exceeds the critical angle, light reflects entirely back into the denser medium. This phenomenon is known as total internal reflection. Once again, this is not a new rule, it emerges naturally from Fermat's principle. We can now see the unifying idea behind geometrical optics. Reflection, refraction, Snell's law, and total internal reflection all arise from a single principle: light chooses the path of least time.